stuff, just matching. How do you guys feel about this? What's a subset of the population called? Sample? Thank you. Do y'all agree? Okay. How about degree of uncertainty? What would we call that? Okay, awesome. I got 2 of those. Set of all units being studied. I'm sorry? Okay. Characteristic of an individual population unit. And then our inference. Sorry. 1 second. So just, I don't think there's anyone new on this side, but yeah, again, if you have a question and I don't see your hand raised, just let me know. Okay, so there we go. Now, here we're identify the population, variable, sample, and inference in the following examples. So go ahead and read that and let me know when you get an answer. I will be posting this with the answers after, so you don't have to like furiously try and write every question. So what's our population here? Awesome, 10,000 plates. And our variable, oh, well, here, I'll put this. Okay, good. Sample, and then our inference. I'm sorry? Awesome. So the mistakes in all plates. Does that make sense? Okay, awesome. Do you guys feel comfortable with that? Finding the inference, population, all that stuff? Okay, cool. So then, what kind of variable do we have here? The heights of students in a class. Continuous? Okay, why is it continuous? Okay, awesome. So then the number of people in a household. And so what's the difference between discrete and continuous? Okay. Okay, good. Does that like flow with everyone? Good with that? Okay. So classify the following as either qualitative or quantitative methods for describing a set of data. So we have, what do we have here? Okay. And is it qualitative or quantitative? I'm sorry? Qualitative? How come? Okay. Can anyone reason why a bar graph would be qualitative versus a histogram being quantitative? For which one? Okay, so categorical values, good. And then a histogram, what are our like classes usually? Good. Yeah, so there'll be no like breaks in between, whereas these have like no relation really, right? So what about this? What do we have here? I'm sorry? Okay, good. So we have stem and leaf. And what is it, qualitative or quantitative? Okay. Are we all good with why that's quantitative? Okay. And finally, histogram, what did we say that was? Good. Are we good with this page? A blank is one of the categories into which data can be classified. Okay, good. Do we all know we're all good with that? Class? Okay, awesome. Now we're going to do class frequency and relative frequency. So how many classes do we have? Okay. So we have 5 classes. And what are those classes? Okay. So we can just okay. And what is our how do we determine the frequency of each of those classes? Awesome. So what's the frequency for the red? And then the blue? Pink? Green? And our yellow. And now, how do we determine relative frequency from that? Awesome. And what's our total? $24? Okay. So 24 is our total. And then you said just divide by the total? Right? Okay. Did we get those numbers? 0.375? Okay. So that's just what you do for the rest of them. That'll be your relative frequency. Good. Okay. Yeah. Do you want to do that real quick? We can do it if you want. But yeah, very good point. So need to add up to 1. Or else there's a mistake in there somewhere. Recount your frequency. Okay. So here we have the same type of problem if you want more practice with that. What is the equation for sample variance? Oh, sorry, yeah, I see what you're saying. Is that not right? So are we good with this? Sample variance? Okay. So now find the standard deviation for the following data set. How do we do that? Okay. So go ahead and do that. So what does, well, first off, what does this read then? What would we do here versus here?
So for that one, you square each number individually and then sum them. And then for the other one, you sum all the numbers first and then split the result.
Okay, awesome. Thank you. Did anyone get that number? Awesome. So now we can go ahead and do our sample variance, right? So, okay, yeah. So I was just going to write this out, minus 2, 3, over, and what's our n? You both changed your answer. Okay. And what does that give us? What did you say? 99.27. So is that our standard deviation? Good. .96. Okay. All right. And now, is the age of 54 an outlier? How do we determine whether it's an outlier or not? Awesome. And how do we find our z-score? Okay. So our, so our x would be what? And our mu? And our standard deviation? Oh, is it? Oh, 875 here? And what does that give us? Great, thank you. So, can we say that 54 is an outlier? Yes? How come? Okay, does everyone agree? Everyone agrees? So this will be a possible outlier. Because anything that's beyond 3, we can say with certainty would be an outlier. So this is a possible outlier. Exactly. Are we good with this? Good. So now we have this set of data, and we're given our R and our, this is an alpha, looks a little wonky here, alpha of 0.01. And the question is the relationship significant? How do we determine that? So this is from, I believe, chapter 1. It was your correlation and regression, if you have your notes on that. Yes, I believe it was on your final exam review. Oh, I'm sorry, what?
Back in the first test, there was a question on that.
I don't know. Do you guys remember if there was a question on it?
It wasn't exactly this, but it involved all.
Okay. Okay, good. So, yeah, that's how we determine if it was significant. I think on your exam, she gave you something, was it like an Excel spreadsheet, and she like asked you, you don't remember?
No, she just gave the R, and it was like, if it was between 1 and -1, then like, whatever that is.
Then it was what?
I don't know, but it was involved the -1 and 1. With the R value, the max, if it was like, I don't know, if it was stronger, yeah.
Okay.
If it was stronger, not.
Okay, so then from here, I think you mentioned it, how we would figure out, is it significant? What do we need to do then?
You have to find the absolute value of the mean, and then if it's greater than the values.
Okay, so here you'll need to use your, I think you have a table for this on your pink. Do you guys have your pink tables?
Yeah.
On there, you can look up whether the R, so using, is that this one? Let me just make sure. Yeah. Bless you.
The critical value, the correlation.
I believe so. What's on that pink table? I never got to see one of those. So, because I just know you have to look it up on there. Good. Okay. So then we have the number of pairs, which is how many? Okay. So we have 9 pairs. And our alpha of 0.01. And so now we can look that up on there. 0.798. And what do we need to do with that value to determine whether this is significant or not?
Check if the absolute values are greater than critical value.
Good. So so our R, 0.963, right? Is this greater than or less than? Okay, so what does that tell us about the relationship? Good. Did everyone follow that? Okay. Any questions on it? So can you just like talk through how you found that on the table? Like what did you have to do?
So the n is 9, so the n column go to 9, and then it has the alpha 0.01, and you match it. And you find the
Good? Okay. So could I make a prediction about y when x equals 11? Why not? Good, awesome. So, no, it's not in the range. And this example she used in class was, say for example you have a correlation of age and height. You'll have that increasing from like ages 0, oh my gosh, okay. From 0 to like 18, and then you'll just plateau. So if your x is just up to 18, you can't really use that same equation you get to make to make a prediction about what, like past that. Does that make sense? Yeah? Okay, good. So what are your chances of winning the Florida Lotto given that you must pick 6 numbers from 53? Awesome. So we'll use our combinations rule, and what is that?
Capital N factorial.
What'd you say?
Capital N factorial. Over lowercase n factorial. And then capital minus lowercase in parentheses with a factorial on the outside.
Okay. And what is our big N?
53.
Little n?
6.
And what does that give us? 22,957?
Probably not 1,000, I said it wrong, but 957 and column
488?
480. No, 480.
480, sorry. Okay. So 22,957,480. So this will just come down to recognizing what counting rule you're using, because otherwise you can just write it on your form, or you probably have it already, right, from your other exam. Okay, are we good with this? Determining how we knew that this was combinations? And then how many ways can you distribute a gold, silver, and bronze medal between 11 people?
So that one's a partition.
Okay, why is it partitioned?
Because you have assigned groups.
Okay, so going back to the combinations, did the order matter in that? Okay, does the order matter here? And what's the only rule in which order matters? Good. So since this one, that's a really easy one when it does matter. That's your only counting rule that matters. So, you know, it'll be permutations. So what's the permutations rule?
For this one, order does matter.
Yes. Can you see why?
So
So say if you have gold, silver, and bronze, it's first, second, third place. So in that case, it matters, like, the order in which the people are going. So what is that?
Capital N factorial over parentheses, capital N minus little n, and then outside the parentheses.
Okay. So what's our big N and our little n? Good. How much? 990? Okay. Good. And then how many different ways can you arrange 7 books on a bookshelf? What rule is that? Partitions? How come? When do we use partitions? Does anyone know? I'm sorry? No.
Not specified, it's just saying 7
Okay. So if it's not specified, we don't have the big N, little n, right? What can we use? Awesome. The multiplicative rule. And what do we do when we have the multiplicative rule?
Multiply like 7 times 6, keep going all the way to 1.
Okay. So just like that?
Yeah.
Good. Wait, so it would actually, well, so here's the thing. This would be, yeah, so this would be 7 factorial. Is that, hold on. I'm sorry? Yeah, okay. So that's what we would, in this case, we can do this, right, for the multiplicative rule. And then for this, what rule is this? Good. The difference in this one being what? Yeah. So this would just be the 3 times 4 times 6, right? And that would give us, so that's just a difference in the multiplicative rule of what it looks like. Make sense? Do you feel comfortable like identifying that? Okay. No, because, well, why wouldn't we put the factorial on the second one? Okay, that's a good question. Well, what does our factorial tell us? Like, what does factorial mean? Like, could we use that here? A factorial? Why not? Well, factorial is just when you're multiplying like every number all the way down, right? Like from that number. So we don't, if we did like 6 factorial, for example, that would just be 6 times 5 times 4 times 3 times 2 times 1. but we just want the 3 times 4 times 6, because those are our options. Make sense? Okay, cool. So there are 25 students in a new RSO. The members must pick a president, 4 people in charge of marketing, 3 in charge of volunteering, and 2 treasurers. How many different possibilities are there? Does order matter here? Good, okay. So order doesn't matter, but this is good, okay. So this will be partition. Do you all agree? Okay, and what's that rule? Is that it? Good. So the other students that didn't get picked for one of those positions being 16, right? Okay. And that would just be the different possibilities. How do you guys feel about determining what counting rule you're using? Pretty good? Okay. How is this one not partitions? Yeah. That's a good question. Can anyone answer that? Why is this one not partitions, but this one is? Okay, yeah, so this one we don't have a big N to work with. We're just trying to find the different like combinations of different options, right? Whereas this one, you have like a set group that you're trying to find, like how many combinations from that you can make. Okay, so good question. Go ahead and read this question, and then we'll go through. So what do we need to do here? For both positions are given to females. I'm sorry? Permutation. So is this a counting rule? I see where you like got that from. We were just going over that. I'm sorry? Good. So we're doing probabilities now. So how do we determine like what the probability of both females getting both jobs? So for these, I always like doing a Venn diagram. So we have A and B, A being female picked for the first position and B being female picked for the second. What do we have here in the middle? Okay. Okay, so the intersection, yeah, which means what? Good. So both things are happening. Both A and B are happening, right? So here we need to find this, right? So you said the intersection? Okay. Probability of, and what's that look like? The N? Yeah. Oh, like the, okay, I see. Yeah. And how do we find that?
Probability A times the probability of B.
And what's the probability of A, female being picked for the first position? Good. And B? I'm sorry? Why?
You already picked one female.
Awesome. So now you have less people to pick from plus one less female to pick from. So the 6 out of 11. Good with that? Okay. So that would just be I'm sorry? 32 over 121. And what does that give us in, well, I guess, do you guys remember if she gave this to you in fraction or decimal? Fraction? Okay, perfect. So we can just leave it there. And then what about the second position is given to a male, given that a female already got the first position? Is it? I can't do that in my head. 132. Okay. So, thank you. Moving on to the section B. What does that look like? Probability of what? Awesome. Which looks like what? Okay. So here it would be what? What given what?
So it's essentially just the first half of that first question, so it's A and B over then probability of B.
Oh, okay. But then what does it look like here? Like what with the little line, the vertical line? So both females are being picked? Good, so the complement. So the second position is given to a male, given that a female already got the first position. So which complement do we need to find? B complement. So does that make sense? Y'all remember complement? Okay, good. And now you can, what was the formula for that? Like that? Okay. And what's our, well, we can just go ahead and do this again, right? So our intersect of these two is what? What's the, yeah, probability of, well, how do we do this first off? Separate them like this? Yeah. Okay. So I'll just actually do this off to the side. And what's the probability of B complement? Would it be 5 out of 12? Okay, good. And A, again, yeah. Good. So then we can go over here and just plug it in, right? And what can we do when we have a fraction over a fraction? I'm sorry? Yeah, good. So we can multiply it by its reciprocal. So this is just the same as if she wants the answer as a fraction. Because if you do it on your calculator, it'll just give you the decimal. What is this? Oh, yeah, 7. Does this go into 132? You said 60 over 132? Is the answer? Okay. So 5 over 11? Okay, cool. So that'll be that probability. Got it? Okay. So now the second position is given to a female, given that a male already got the first position. Probability of B given a what? Okay, good. The complement. Okay. So do you guys feel comfortable doing this one? Or do you want to go over it again? I'm sorry? You want to go over it? Okay. So then what does this look like? B given A complement? Like that? Okay. And then we can just do the math again then. And what is our probability of B? 4 over 11? 7 over 11. Okay. Oh, I see. Okay. Because what's our A complement definition of that? Good. Mm-hmm.
So they just divide out the remainder of the probability of B complement anyway. So you just want to stick with a couple of steps.
Okay. So 35 over 132. Does everyone see where that's coming from? Okay, good. So then we can just divide them again. Probability of A complement being... Okay. And then just find your answer with that. We don't have to go over that again. So then what about both positions are given to males? Oh, I'll just keep that there. So you can... Okay, what, like would it just be the conditional again, or what are we doing? Okay, awesome. Do y'all agree with that? Okay, cool. So then you could just go back and, do you want to go through it? Or? Good question. Why? Is it the intersection? Why'd you say that? Good. So now it'll just be, so A complement, remembering that that's just anything that's not A, which is a male, right, getting it? And then anything that's not B is a male getting the second one. So then we just have to, again, find the intersect of those because we want both of them happening. Good? Do you guys want to do this or move on? Move on? Okay. So go ahead and read that question. Are the events independent or dependent? Independent? Why are they independent?
You're independent because when you draw the novel and then you put it back, it's not really gonna, like your first pick or whatever, and you put it back, it's not really gonna affect your second one.
Are you putting it back?
Well, oh, it's not.
Yeah, so not replaced. So what does that mean? Good. Dependent, again, just as a reminder, meaning the probability of one happening is going to affect the probability of the other happening. So are the events mutually exclusive? Why not? Okay. What's mutually exclusive? What does that mean?
Mutually exclusive or always independent.
What do you guys think?
I think they don't share anything in common.
Okay. So do they share anything in common? Do you guys have the definition of mutually exclusive?
Mutually exclusive ones that one can happen without affecting the other. So, by definition, that would be independent, right? So then that would make it dependent, right?
So you're saying, are you saying that they are mutually exclusive or not?
I don't know.
A intersection B equals 0, then A at the end could be exclusive.
Good. So if A intersection B is 0, what does that mean? What does our Venn diagram look like? So they're not intersecting. So do these intersect? Our first bell being red and our second bell being red. Good. Yeah, so they can happen together, right? So does that make them mutually exclusive or not? Not. Good. Do y'all understand why? Okay. Cool. So then 18. What's the probability that none of them get cancer? How do we do that? 3/4 to the power of 6. Why?
Because each individual one, so the chance that they do is 1/4, so then the chance that they don't is 3/4. So if there's 6 of them, you can see like 3/4 is 6 times 3/4, that's 3/4. That's 3/4.
Oh, I see what you're saying. Okay. Does that work?
Or would that be 3/4 to the power?
I think she worked it out differently.
I think you can do like 1 minus, or like 3/4.
So,
1 minus 3/4 to the power of 6.
like that?
Yeah.
Do y'all agree with that? So this is similar to the sickle cell anemia problem she loved so much. You guys remember that? How did she find these probabilities? Just keeping in mind this, another way of writing this, if none get cancer, that means our x equals 0. Make sense?
So it would be like, the x would be like 0, and then like, all the way up all the way to 6. For each column, would be the 6.
Okay.
And then the bottom would be like the probability. So like, for this one, the fraction was like 27 or 65.
27 over 64.
Yeah, for this example, not that.
Oh, I see, okay.
But I'm not sure how she got this.
Okay. So, do you guys have your notes on this? Okay, good. So, yeah, so the 3/4. Okay. And then do you do the 1 minus? Okay, good. Because 1 minus that would give us, yeah, good. So the chance that like all of them get it. So, yeah, we can just do that. What does that give you? 3/4, so 1/6. 0.177. Okay. So then that is our probability of x equaling 0. Okay. And then the probability that 2 get cancer, what's that? To the what? Okay. Does that make sense to everyone? Okay, good. Did anyone do it or trying to do it? Did you get?
Exactly one acquires the disease, she does the probability for one to get it plus probability for the second to get it and not the other two.
I see what you're saying.
Yeah.
Okay. So what he's saying is we would have to do, you said like the intersect, you would say, right? Or what did she?
Yeah. It's the probability of basically the two complements and one non-complement. So, so she did C1 instead of C2 complement instead of C2 complement.
And what is our C?
You have to do 6 times. C is a child.
Okay, I see. So then what's the complement of the child? Like, so what's our, so this is where we do the success and failure. You guys remember that? So then what here is our, like what's our success in this? Yeah, so success is that they get cancer, so that'll be C, our definition is child gets cancer, right? Or person gets cancer. So then now we can do that of the, you said person gets cancer, right?
I don't know if you can do that problem with what we have, because she only had 3
Yeah.
so if you have 6, you have to do, the first one gets it, and the second one gets it, plus the first one gets it, and the third one gets it, plus the first one gets it, and the fourth one gets it, plus the first one gets it, and the
I see what you're saying.
do it for the second one, and the third one, second one, and fourth one.
Okay, I'm pretty sure there's another way you can do this one. Yeah. Good, okay, which is?
N factorial over X factorial parentheses and minus X and cosine.
Can you say that slower?
Yeah, N factorial
The little n?
over X factorial parentheses N minus X and then close it.
Good. Okay. So this is the one we're going to use. the formula, okay? So our n being,
Well, and then P 6. X would be 3.
okay, and what does that give us?
So
15, okay. So the probability that 2 get cancer is 15. Does that make
no, there's more to the formula.
Okay.
I just saw it. It's the P of X and then the Q n minus X
Okay,
at the beginning. So that's probably where they got the 15 from. Because I ended up with like a crazy number.
so P of x and then Q of n minus x? Okay, so let's try that. Hopefully that'll give us a more reasonable number.
So the P is like your successes. So the P in this case would be the 3/4. Because like 1/4 of getting cancer, so then the success. I'm confused. I don't,
What
because I don't
on
want
here,
the
what
success
she
to be
did
getting
was
cancer.
like when you add up like probability, C1 and then like C1 complement.
That's what he had, yeah. Yeah, which is like where the super long thing would go on,
Yeah.
right? So what is this formula good for? What did you like have that as? Because I'm
Oh, that's for
pretty,
binomial and variance.
okay. Is this a binomial random variable?
Yeah.
So can we, use it? Yeah, so this will be a shorter way of getting that same. So then the success would be what? Based off of the question. Because we have to do it based off of the question.
Getting cancer.
Yeah, so then,
P would be 1/4.
okay, so then we do 1/4 to our x being 2, and then our q. And then what does that give us? Would you? Good. Makes a little more sense now, right? Rather than the 15. So I'm assuming then that the C complement, all that stuff can be used, but like if you have a much smaller sample set, because you don't want to have to be doing this like for 6 people. Make sense? Well, this is just, I mean, we can try it out and see if that works. I don't think she ever did it that way, but this here. I'm sorry? Well, you can just do, yeah. It just wouldn't give us that number, I don't think. Are you doing it?
That gives us a different number, but when would we use that one?
Well, I don't. So when, because you want to multiply them, whereas this one, this is like saying that, well, it's because not all of them or none of them are getting it, basically. Because if all or none are getting it, you can use that. But then this one here is just, I mean, I've never seen her use that. I can't really tell you why. Like this is just the formula that works when your x is like not 0, basically. Okay. Are we good with this? Okay. So now assume x is binomial. What do we need to do here? Good. What chart are we using? So then what does at most 4 look like? Good. Awesome. So the chart reads that, so we can just go straight to the chart. The binomial. You all got that? Okay, good. And then at least 4, what does that look like? Greater than or equal to? And so how do we do that if our chart reads this way?
1 minus less than is equal to.
Does that make sense to everyone?
Yeah.
Okay, good. And that gives us what?
1 minus 0.09.
Okay. What is it?
1 minus 0.09.
Good. And then at most 5, that'll just be the same. Less than 3. How do we write that?
No, it's less than equal. It's not the same as less than.
Less than or equal to 4.
How come? Okay, good. So you're trying to like not, basically you don't want the 3 included there, right? So whereas in this case we wanted the 4 included, which is why we could look that up. Here we want just anything below. Make sense? Okay, cool. And then greater than 4? How would we write that?
1 minus 2 of that less than or equal to 4.
Less than or equal to 4?
Yeah.
Okay. And this time, why are we doing the or equal to? Yeah, good. So we want anything greater than. So we're also trying to take that out. Okay, so then this is just a true or false. Do Poisson distribution tables and binomial tables work the same way, as in like with the less than or equal to? Yes? Okay, good. So yeah, so they'll work the same way. The only difference will be what? Awesome. So yeah, that'll be a nice one because it'll just say Poisson and you know you can use it the exact same way if you know the binomial. Any questions on that? Okay. So now, let x be uniform from 70 to 85. What does that mean? The uniform. So they have the flat top here. So how do we find f of x? 1 over the 85 minus 70? Okay. Otherwise, like, how would we write that if we just have the, like, formula? Yeah.
1 over d minus c.
Good. Yeah. So 1 over d minus c. That's what that is, if you remember. And that's our f of x. And then how do we find the mean?
It should be 15.
15?
No, 1 over 15. 12.8.
1, sorry, thank you. So 85 minus, what'd you say? What were you going to say?
Oh, I thought you were talking about the second question, because I was going to ask like where you have the 15.
Oh, yeah. Okay. So, thank you. What'd you say? Good. And then our probability that x is greater than 90. How come? Good. So it's beyond this. This is all we're looking for. How about less than 80? This will be another formula. Okay. So less than, where are we shading? So then you said our B is 80, and then our A? Good. Good. And what does that give us? 2/5? 2 over 3, okay. And then what is the probability that x is greater than 65? Draw this out again. Awesome, yeah, so our 65's out here, right? Is there anything over here? Any probabilities in here? Good. So it'll just be everything. So that'll just be 1. Make sense? Okay. Go ahead and read the question. How do we construct a 95% confidence interval? Okay.
The sample is 120, so it's like large enough. So you do mean plus or minus the z times standard deviation over radical.
Plus or minus what?
The
Z what? What?
like the
Good, yeah. So this is our alpha over 2z.
times the standard deviation.
Oh,
Well, only the n has an alpha.
only the n has the square root. Okay. So times the s.
Well, no, that's for a small sample. It's
The sigma. Okay, well, yeah. Do we have a sigma here? Because what's sigma? Of what? Good. So our population. So in this case, we will be using the S because it's the sample standard deviation. So times S and then square root of n. Okay. And what's our Z alpha over 2? Okay. And what's our Z alpha over 2? 1.96, okay. And our x bar?
16.2.
Good. And what does that give us?
You just want the full of, like just the right side of it, you want it to be, or the whole?
Oh, either one.
Because I got for like the right side of it, it'll be plus or minus 0.64.
0.64? Is that what you said?
Yeah.
Okay. And that'll give us the interval, right?
So the upper part would be 60.32. The lower part would be 15.56.
Point what? 0.56, okay. And how do you interpret that? Good, okay. Awesome. Are we all good with that? Go ahead and read that question. So what kind of problem is this? Good. So we have a proportion problem where we're trying to find what? Okay. So we're trying to find that confidence interval. So how do we do that with proportion? Okay. And what's our p hat? And what's our x? The 671? Why is it the 394? Good. So then, what is that? Making our q hat. Awesome. So now what can we do? Check what? Good. So you said n times p hat, and what else? Greater than 15. And are they? What's our n? Good. The 1065 times our p hat, 0.37. So what is that? Checks out? Okay. And we know the other one's bigger, so check out. Good. So then what can we do? And is the n under the square root as well? Okay. Don't have these formulas all memorized. So then, what's our z alpha over 2 here? And what does that give us? That's a good question. Why did we use the 394 instead of the 671?
Oh, because it's about the method is not beneficial, not looking at it.
Yeah, because it's the confidence interval for the proportion of people that said it is not beneficial. So not beneficial are the ones, the 394. Does anyone have that interval yet? Oh, for this part? Okay. Okay, good. So can you conclude that less than half of all parents don't believe dogs are good for children's emotional development? I'm sorry? No. No, yes. Why? Good. So we can conclude that less than half of parents don't believe it, because if we had anything 0.5 or above, that means that that is a possibility as well, right? So yeah, that's why. So we can't make that conclusion. Does that make sense to everyone? Okay, good. We can. And it's because. Do you see why? Okay. Okay. So go ahead and read the question. So what are we trying to find here? Good. Sample size for what? Proportion or mean? Is it for, okay, why is it mean? Good. So we need a sample to find the average shoe size. So then how do we do that? It's what? N equals? Okay. So what's our Z? .33. Why? Good. Yeah, so you want to find your Z from that. So is that one of the numbers she gives you, the critical values? Okay, good. Yes. Good. So that's the 2.33? Okay. And what's our sigma? Does everyone see where those numbers are all coming from? Okay. 87? Okay. Good. And just remembering to always round that to a whole number, the round up, right? Okay? Did everyone get A7? Whoever did it? Awesome. So a medication used to treat arthritis. Oh, go ahead and read it. I need to meet you to read it to you. What kind of question is this? I'm sorry? Okay, good. So large mean. Testing hypothesis. Do y'all agree? Yeah. Good. So what are our steps for testing the hypothesis? So what's our step 0? Okay, do we have any assumptions here? Good. Anything else? Okay, yeah, because our CLT is applying, so our, it's normally approximately normally distributed. Okay. So then our step 1. And what is our HO? $410? That's our null? Yeah. Why? Why is it not 410? Yeah, so this is like the claim. So our null hypothesis is what the original company is claiming, right? And then what's our alternative? And why greater than? Good, that there's more. So always look at those keywords to tell you what's happening for your alternative. And then what's our third step? And how do we find that? Over sigma divided by what? Okay. And our x bar is what? And our sigma? $45? Well, I mean, I'm sorry? I may have not given you a sigma here. We'll just say that it's, let's see, we'll say 5, okay? Our sigma is 5, because I didn't put the sigma here. Okay, so, and then our n? Good. And what does that give us? 13.42? Okay. So then what's our step 4? So how do we do that? Upper tailed? Okay. Do y'all agree? So this way. And where does our test statistic fall? And what's over here? Why is it 1.645? Good, yeah, so that's sort of the significance level, that's alpha of 0.05. So 1.645. Can we reject null? Yeah, what's up? Mm-hmm. The alpha. 1.96? Why? For the 90%? Okay. Yeah. So was that for the 90, the 1.645? For the two-tailed 90. Okay, so remember we're looking at the one-tailed. Okay, good. So, okay, so this is our rejection region from 1.645 on. So did we say we can reject HO or not? Okay. Can reject HO. And what is our number 5? And how do we word the conclusion? Mm-hmm. Good, and then you would just word the question in those terms. Okay, and then number 26. No, I just gave us more room. There's like, they each have like their own paper. Yeah. Okay, what kind of hypothesis test? Okay, how come? Good. So we are using 205 out of 510, right? There's a 70% chance they'll buy more food than they need. So those all those things tell us we're doing proportions. So how do we do that? This. Step 0 is what? Do we have any? Greater than 15, okay. And what's our, well, what needs to be greater than 15? Okay. And what is our p hat? Okay, which is, what's our success in this case? The what? 0.7, is that what you said? Good, yeah. So you do the 205 divided by 510. So you said 0.4? Mm-hmm. Okay. And then is the 0.4 times 510 greater than 15? Checks out. Good. And that should check out. So then what's our null hypothesis? P equals what? I'm sorry, what did you say? 510? 0.7. Why is it 0.7?
That's what was given.
Good.
So, and the alternative is not equal to 0.7 since they're asking if 7.7 is incorrect.
Do y'all agree with that? Again, with those keywords, is it incorrect? So it'll be two-tailed, right? And how do we find our test statistic?
So it's C equals P hat minus P naught over square root of P naught times P naught all over n, and n is under the square root.
Okay. And what's our p hat? 0.4. And our p naught? Making our q naught what? And our n? Good. So what does that give us? Yeah, for these they are. That was just. So you're saying it would be the 0.7?
Well, because you put
Yeah.
them as like P hat and Q
Mhm.
hat. But I have them like P naught and Q naught. Maybe I don't know if I like wrote it down wrong. Like, does it make a difference, honestly?
It could potentially.
I really think these close, so I think I'm going to get these on point.
What'd you guys?
Yeah.
Okay. So that's the right formula? Okay, so I wrote this question, I put my own numbers. so that it could potentially be negative 14, 7, 8, okay. So then our rejection region, what's our graph look like?
Well, it's
Two-tailed.
So for 99%, so that's 2.579.
Okay.
And so negative 14.7, that's followed by 90. So
Yeah, so that's way over here.
we would return.
Good. Awesome. And then the conclusion.
There is insufficient evidence to suggest that P equals 0.7.
Okay. Is that how we would word it? There's insufficient evidence that P is equal to 0.7? Good. Yeah, so remember at alpha equals 0.01, sufficient evidence to reject. Make sense? Okay. Any questions on any of that? Okay. Go ahead and read that. 30?
Already looked from this last chapter.
Yes, actually, the last two. Do you want to skip this one? Do you want, okay, cool. Go ahead and read it. So what kind of question is this? Okay, good. So they're independent random samples. And is it mean or proportion? Mean? How come? Good, yeah, so this will be a proportions question. And it's comparing two groups, right? So how do we start this? So this will be the confidence. No, that's using a 90% confidence level. It's asking, is there a difference between the sexes on their support of affirmative action? So what is that asking? Yeah, so that'll be the hypothesis test. That both are large. Okay, so that'll be our step 0. How do we check if they're both large? Do you guys have your notes on this? Like, this is... equal to 30, okay. And is it? Not for N2. So this is not. So then what? I'm sorry? Okay, yeah, so this will be one that you can't continue. But let's say that this instead is 30. We'll just change it to 30 so we can go through the problem. So what's our null? Is it P? Good. Yeah. Sorry, I thought you said not equal. Okay. So then, what's our HA? There is a difference. Good. And then how do we do the test statistic? Okay. So it's our P hat 1. For p hat 1? How do we find that? The p hat 1. Okay, good. So for the 1 being, we'll do the females, right? What do you need to divide? And that is 0.83? Mm-hmm, yeah. And then our 2? Okay. Oh, yeah. So is this, what p hat is this? Mm. Good. And what x's are we adding? 26 and 30? Okay. And our n's? Good. And what is that? Which is 0.70, making our q hat what? N1. Good. And what is that? Did everyone follow as to why the difference in p, why it's equal to 0 for our null alternative is not equal to? Okay, good. Okay, 1.348. Okay, yeah, we can just do that. And then our step 4, what's our rejection region look like? And is it, where is that going? The, okay. Okay. Because, yeah, our 1.35 would be here. And then what's our conclusion? Okay. Meaning what? In terms of our question, how would you word that? Good. Did everyone follow with all of that? Okay. So as you can see, there's not much difference between this and the Chapter 8 hypothesis testing. It's just mostly realizing like what your HO and HA are, and then the rest is just using your formulas. Okay. So go ahead and read that. Oh, did I not? I didn't write any of the numbers. Hold on. What is that? One second, guys. I'm going to pull it up here. I have the numbers here, and I'll just tell them to you. Okay. So and I also did not give myself enough boxes. So it'll be 3 and 4. Yeah, what's up? Yeah, if we have time. It was what? 27? Okay, yeah, that's fine. So, 6. So how, seeing like, I'm giving you the numbers, start thinking about like how are we going to do this? Is there evidence to show a difference in wear between the brands? So what will we be doing? I'm sorry? Okay, good. So we have a pair difference, and how do we go about that? And I'll post this with the numbers in it. Okay. So is this, okay, so approximately normal? Good. So our sample size is small, so we're using T. And what's our HO? Which is what's our D naught? What? 0? Why is it 0? Good. And our HA? Awesome. So then our test statistic. Minus D naught being ND? The D naught? Is that right? Oh, I see. Okay. Great question. Why did we want to use 0 here? And not 0? The D, okay, and why is the D 0 for the null? Good, yeah, so the question is there a difference? So, because it's asking, like, that's your alternative hypothesis, so if there's a difference, it'll be not equal to 0, because anything that's not 0 would be a difference. Make sense? Okay, good. So here we have this, I just figured it out for you guys, was from that, minus our 0. And what is our ND? Oh, my bad. Okay. Do y'all agree? Okay. So it'll just be like the pairs, basically number of pairs. And what does that give us for a test statistic? Okay. And then our rejection region. Okay, and our test statistic is way out here. Okay, and our conclusion? So how would we word that in terms of the question? So yeah, there's evidence to show a difference in where between the two brands. Make sense? Okay, so that is all the time we have. I will post the ones that we didn't complete. I'll post the answers to that as well. I'll post it on the Study Union site. It's just if you look up UCF Study Union WordPress, it'll come up. I do real quick, if you guys could just fill this out for me. It's super quick.